I'm Carolina Marques. I'm a PhD student at the University of St. Andrews, and in this video I'd like to show you a bit of the research I have been developing on finding new emergent orders at the surface of strongly correlated electron systems. Currently, there are three main technological limitations. The losses in energy transportation, with the world only using about 30% of the total energy it produces. The fundamental limitations in information processing, such as processing speed and energy consumption, where companies like Google and Microsoft are spending enormous amounts of money and energy to speed up their processors and to cool down their servers. And finally, the large demand for memory storage, with platforms like Netflix and Amazon Prime having fast expanding libraries. These limitations are set by the intrinsic properties of silicon-based electronics and the use of materials with finite resistance in electric circuits. The solution to overcome all these challenges rests in strongly correlated electron materials. To give an idea of what I mean by strongly correlated, imagine you are listening to music. Here I will play a track of someone playing the piano, and I plot the power spectral density of the Fourier transform as a function of time and frequency. You can hear the individual notes and melody, and you can see the beats appearing in the power spectral density as the notes are played. Now what I'm going to do is to remove the time correlations of the signal by putting the phase of its Fourier transform to 0, and then I will gradually turn on the phase until the original signal is recovered. That is, until the time correlations are restored. Listen to what happens. When the signal was uncorrelated, it sounded like outer space and boring, but when the correlations were restored, you could hear exciting sounds creating music. This is what we have in condensed matter physics. On one side, we have materials where the electrons have no correlations between them, and you have normal metals like copper, semiconductors like silicon, and insulators like PVC, which are the base of our current technology. And on the other side, you have materials where the electrons are correlated and show exciting physical properties like superconductors, metamagnets, and Mott insulators, which you can find, for example, on transition metal oxides, like strontium ruthenate 214. This material is an unconventional superconductor below 1.5 Kelvin, and for over 20 years people thought it was the most promising spin triplet superconductor to be used as a platform for quantum computations. And although recently it has been proven that this is not exactly the case, its superconducting area per meter remains one of the biggest puzzles of modern research. Its properties are highly sensitive to tiny structural distortions, with a large variety of ground states available, as exemplified by looking at its family members from the Rulus-Den-Popper series. Upon increasing the number of ruthenium octahedra at the center of the unit cell and including rotations, the superconductivity seen in 214 is suppressed, giving way to its inherent metamagnetism and quantum criticality, different ferromagnetic and metamagnetic phases, and isotropic ferromagnetism. Insight into how these distortions are responsible for the stabilization of such a diversity of ground states will allow the control and optimization of the properties of these materials, opening up the opportunity for the development of novel devices. The best way to do this is by distorting the simplest system, a single layer of strontium ruthenate 214. And luckily, we can find this system by looking at its surface. When cleaving a single crystal of strontium ruthenate 214, the group of Earl Ward Plummer found that the surface layer undergoes a reconstruction, where the Ivy League pattern shows additional spots corresponding to a doubling of the unit cell due to the in-plane rotation of the ruthenium octahedra at the surface layer, in contrast with the bulk which shows an undistorted structure. This is a consequence of the bulk having a structural instability towards octahedral rotation, which freezes at the surface layer. This rotation dramatically changes its electronic structure. The Fermi surface of the bulk shows three bands due to the 4D states of the ruthenium atoms, alpha and beta of dxz and dyz orbital character, and gamma of dxy character. I can reproduce this with EFT calculations on a single layer, and the most interesting part of this band structure is the presence of a saddle point at the gamma band above the Fermi level, which we call Van Hove singularity. When you include octahedral rotations in these DFT calculations, what happens is that the Fermi surface has 6 bands due to the doubling of the unit cell, and the band structure shows that the Van Hove singularity has moved below the Fermi level. However, the consequences of this shift to its ground state are unknown, and in order to understand it, high-resolution spectroscopic information is crucial to provide a complete picture of the low-energy electronic structure of the surface layer of strontium ruthenate 214. The goal of my thesis research is to establish that understanding through scanning tunneling microscopy, or STM, at ultra-low temperatures, unraveling the secrets of ruthenate physics. For this work, we use an STM coupled to a dilution fridge that can reach temperatures below 100 millikelvin, allowing for sub-millivolt energy resolution. With these instruments, we are able to clearly resolve features as sharp as the superconducting gap of tin-4 arsenic 3 with a width of 190 microvolts, and so it is ideal to study the low energy states of the surface of strontium ruthenate 214. So what do we see? The topographies of the surface of strontium-214 imaged at positive bias show a square lattice corresponding to the strontium atoms appearing in the Fourier transform has peaks at 0 to pi. The defects at the surface have two distinct rotations, confirming the presence of the surface reconstruction. The tunneling spectrum shows a partial gap around the Fermi level instead of a clear peak due to the Van Hove singularity. High-energy resolution spectrum measured at 76 millikelvin reveals the presence of 4 peaks surrounding the partial gap. We see 2 inner ones and 2 outer ones, as indicated by the red arrows. By imaging close to the energy of this peak at -5 millivolts, the topographies show a modulation on top of the strontium lattice, with adjacent strontium atoms appearing with different intensities. This is reflected on the Fourier transform, has strong peaks appearing at the pi-pi positions. To understand the energy dependence of this checkerboard modulation, we look at the differential conductance maps in a small area where we take a tunneling spectrum at each pixel of an image, resulting in two-dimensional real space images of the local density of states. We observe that, although the topography at positive bias does not show such a modulation, the differential conductance layer at -3.5 millivolts shows a strong checkerboard, and that at +3.5 millivolts, a checkerboard is also visible, but with opposite phase. To extract information about both the magnitude and phase of the checkerboard as a function of energy, we can look at the phase of the Fourier transform at the pi-pi peak, like I did in the beginning with the music. To see the phase changes, we divide the phase at each energy by the phase at -3.5 millivolts, such that positive values in this plot indicate in phase and negative values indicate out of phase with the checkerboard at -3.5 millivolts. We see a strong peak centered at -3.5 millivolts and another peak with negative value at +3.5 millivolts, corresponding to this phase shift. Both have a width of about 1 millivolt, showing that this order is highly localized in energy and so it must be of electronic origin instead of a pure structural shift of the strontium atoms. The phase shift is consistent with the charge modulation. The energy position of the checkerboard corresponds to the intensity modulation of the two inner peaks observed in the tunneling spectrum. In addition, these differential conductance maps show the appearance of unidirectional patterns at certain energies. While outside the partial gap, the patterns are C4 symmetric. As we approach the Fermi level, the electronic density is observed to align and switch between the 1, 0 and 0, 1 directions. This is also observed at the quasi-particle interference pattern surrounding defects. Again, outside the partial gap, the patterns look C4 symmetric. But as we move across the Fermi level, they align along the crystallographic directions, switching between them. These results show the presence of two orders at the surface layer of strontium-214, checkerboard charge order and C4 symmetry breaking of the low-energy electronic states, which become equivalent via the octahedral rotation. We can phenomenologically include these two orders into a tight binding model via charge modulation to describe the checkerboards, and an equivalent hopping between ruthenium atoms along the 1, 0 and 0, 1 directions to describe the C4 symmetry breaking or pneumaticity. This phenomenological tight binding model shows a gap opening at the gamma band around the Fermi level, with the appearance of 4 Van Hove singularities indicated by the red arrows. The density of states of this model is in excellent agreement with our experimental tunneling spectrum, reproducing the partial gap and the 4 peaks around the Fermi level, establishing them as Van Hove singularities. Recently, we have confirmed this interpretation from quasi-particle interference and using realistic modeling of the tunneling spectra in this publication. Now that we have a Van Hove singularity, we expect it to Siemens split when a magnetic field is applied to the surface. To do this textbook-like experiment, we applied magnetic fields up to 13 Tesla and looked at the behavior of this Van Hove singularity. As the magnetic field is increased, the peak splits with one of the branches moving towards the Fermi level. We track the position of the peaks as a function of applied magnetic field and find that they follow a linear trend consistent with Siemens splitting. This analysis gives us a G factor of 3 consistent with the Wilson ratio of bulk strontium-214. If a Van Hove singularity reaches the Fermi level, something exciting is bound to happen. So we extrapolate our fits, and the Van Hove singularity is expected to reach the Fermi level at 32 Tesla. Reaching this point will lead to a Lifshitz transition and potentially to quantum criticality. If we were able to do this, the surface layer of strontium-214 would be the perfect clean system to directly measure the shape of the Van Hove singularity peak in the density of states as it approached the Fermi level and might help understand the effects of quantum fluctuations in approaching a Lifshitz transition. So how can we push the Van Hove singularity even closer to the Fermi level? ARPA's measurements have shown that the bulk Van Hove singularity can be pushed towards the Fermi level by applying uniaxial strain. So by combining uniaxial strain and magnetic field, we will be able to track the changes to the Van Hove singularity of the surface as it crosses the Fermi level. This will allow us to determine if the surface becomes quantum critical, and it will help to understand how these tiny distortions to the lattice stabilize different ground states, interchanging between the properties of the different Rudolph-Popper series members. There are two big puzzles remaining. The first one is that we do not observe a superconducting gap at the surface, suggesting that the octahedral rotation suppresses superconductivity, which might have implications on the allowed pairing mechanisms in the bulk. The second one is that we observe the stabilization of instabilities already present in the bulk at the surface layer of strontium-214, which opens up the question if this is also something that is happening at the surface of other members of the Rudolph-Popper series, and what kind of new states can we find? Finally, I'd like to thank everyone who made this work possible. Thank you for watching.